Hey guys, this is 3.3 notes. Hopefully you've already tried the warm-up. If not, go ahead and pause it and do your warm-up. Okay, so let's look at number 1. Use logarithmic differentiation to find the derivative of y with respect to x of y equals 2x over radical x squared plus 1. Okay, so this is a great candidate for logarithmic differentiation because it's such a complicated function, and we would have to do quotient rule, chain rule, lots of different crazy things. So let's try it with the logarithmic differentiation. So the first thing we're going to do is take the natural log of both sides. And then what we want to do is use our log rules to simplify the right. Okay, so I know that when I have division, that becomes a subtraction. And notice I'm rewriting this with the square root as a half. Okay, and then I know also I can bring this 1/2 down in front. Okay. All right, so now I'm going to go ahead and do my derivative. So the derivative of natural log of y is 1 over y dy dx. On the right, I have natural log of 2x, so that would be 1 over 2x times the derivative of 2x, which is 2, minus, and then I have to go down here a little bit, a half, and then I have derivative of the natural log of x squared plus 1, which is 1 over x squared plus 1, times the derivative of x squared, which is 2x. All right, a couple of things can cancel here. My 2's, these 2's. Okay, so now let's see. I'm going to come down here. So I have 1 over y dy dx equals 1 over x minus x over x squared plus 1. And then the last thing I want to do is times by y on both sides. And so my final answer, dy dx, equals 1 over x minus x over x squared plus 1 times y, which was 2x over square root of x squared plus 1. All right, number 2. The total surface area S of a right circular cylinder is related to the base radius r and height h by the equation S equals 2 pi r squared plus 2 pi r h. All right. All right, so number A, we are going to see how ds dt relates to dr dt if h is constant. So when it says h is constant, it just means that when I do the derivative of that part, I do not have to have a dh dt involved, okay? So this would give me the whole derivative. I would have ds dt equals, okay, so derivative of 2 pi r squared would be 4 pi r dr dt plus, and now here I do have to do the product rule. Okay, so I have derivative of the first, which would be 2 pi times the second, h, and then I need my dr dt because that was the derivative of r, plus, and now derivative of h is 1, so 2 pi r. And I don't need the dh dt because they said h is constant. All right, B, how is ds dt related to dh dt if r is constant? Okay, so we're basically doing the same thing again. This time we don't need the dr dt and we do need the dh dt. So ds dt equals 4 pi r plus 2 pi h plus 2 pi r dh dt. Okay, and then the last one, how is ds dt related to dr dt and dh dt if neither r nor h is constant? Okay, so it's basically the same thing we already did, and we need all of the variables represented with their derivatives. So ds dt equals 4 pi r dr dt plus 2 pi h dr dt plus 2 pi r dh dt. All right, there we go. Okay, so today we're doing increasing and decreasing functions. The lesson takeaway is, oh, there's a typo here. Okay, so the lesson takeaway, I'm missing an A. It's supposed to be as a corollary. Okay, so right here, as a corollary to the mean value theorem, we see that functions with positive derivatives are increasing functions and functions with negative derivatives are decreasing functions. And that should make sense to you. If something is increasing, all of the tangent lines are going to have a positive slope the whole time, right? And if it was decreasing, then all of these would have negative slopes the whole time. All right, definition. A function that is increasing or decreasing on an interval is said to be monotonic on that interval. So basically, if it's only increasing or only decreasing, it's called monotonic. Mono means one, and so it's only one way, going up or going down. All right, let's look at a corollary here. Suppose that f is continuous on AB and differentiable on AB. If f prime of x is greater than 0 at each point, then f is increasing. And if it's less than 0 at each point, then it is decreasing. That's basically what we said from the lesson takeaway. All right, let's look at example 1. Find the critical points of f of x equals x cubed minus 12x minus 5 and identify the open intervals on which f is increasing and on which f is decreasing. Okay, so we're going to start by finding our critical points. If you remember from 3.1, the way that we do that is by doing the derivative and setting it equal to 0. So we're going to do f prime of x equals 3x squared minus 12. Set that equal to 0. Add the 12. Divide by 3. So positive and negative 2 for x. All right, and so at this point, we are going to go ahead and test values. So we're going to make a little number line here. We have our negative 2 and our positive 2. Remember, other critical points would have been where x would be undefined. In this case, we didn't have any, okay? But remember, if you had something like 3 over x, right, as your derivative, then you would want to test 0 as well as an undefined point. Okay, so we're going to test values. Remember, you are plugging the values into the derivative, not the original function. All right, let's try 0. F prime of 0. So if I plugged 0 in, I would get negative 12. Okay, so what that means is that in this interval from negative 2 to 2, since 12 is negative, this is decreasing. The function is decreasing here. All right, let's look at f prime of 3. Okay, so if I have f prime of 3, 3 squared is 9. 9 times 3 is 27. 27 minus 12 is 15. Positive. So increasing. And then how about we do negative 3? Since x is squared, it's going to give me the same value as f of 3 because it gets rid of the negative. So 15 again. Positive, increasing. All right, so let's write down f is increasing on negative infinity to negative 2 and 2 to infinity. decreasing on -2 to 2. And if you were to look at this function, you would see that it is a cubic function. Looks like this. I actually don't think it goes through 0, 0, but you can see here increasing, decreasing, increasing in those intervals. Okay, so at the bottom here, it's the first derivative test for local extrema. Suppose that C is a critical point of a continuous function f, and f is differentiable at every point in some interval containing C, except possibly at C itself, moving across this interval from left to right. If f prime changes from negative to positive at C, then f has a local minimum at that point. Okay, so if we're going decreasing to increasing, that's a minimum, okay? Next one, if f prime changes from positive to negative at C, that's a maximum. Okay, so it was increasing, then it was decreasing. That's a max. That makes sense. And if f prime does not change sign at C, then f has no local extremum at C. So if it was increasing and then it continued increasing, then there's no max or min at that point. By the way, these were supposed to be bullets. So there's no point to the numbers there. All right, let's try example 2. Find the critical points of f of x equals x to the 1/3 times x minus 4. I kind of simplified it a little bit for you there. I just distributed the x in, so x to the 4/3 minus 4x to the 1/3. Identify the open intervals on which f is increasing and decreasing. Find the function's local and absolute extreme values. All right, so we're not only doing increasing and decreasing here, we're also doing maxes and mins. All right, so let's go ahead and do our derivative. So f prime of x. I'm going to use this one because it's just power rule and I don't have to do product rule here. Okay, so the 4/3 comes down in front, subtract 1, I get 1/3, minus the 1/3 comes down in front, 4/3, x to the negative 2/3. All right, so we want to set this equal to 0. We can factor out a 4/3. And since we're trying to equal 0, the 4/3 really does nothing for us. We can divide it on both sides and it kind of just goes away. What I'm going to do now is I actually want to add the x to the negative 2/3 to the other side, okay? So this gives me x to the negative 2/3 equals x to the 1/3. All right, it's important to remember, I'm going to come down here, that this is 1 over x to the 2/3. Okay. All right, one thing I want to notice right now, and I'm going to write it down so I don't forget, I have an x in the denominator, so one of my critical points is going to be 0 because x is undefined at 0. Okay, so I'm going to write that down, undefined at 0. And it's important to remember that because when we're solving for x, 0 is not going to come up as an answer, but it is a critical point. All right, at this point, I think I should cube both sides because what that's going to do is it's going to get rid of this crazy exponents that I have. Okay, so on the left, I get 1 over x squared, and on the right, I get x. Okay, so now if I cross multiply, I get 1 equals x cubed, and so 1 would be the answer. All right, so I have these two critical points. I have 0 and 1. All right, so I'm going to set up my number line. I've got 0 and 1. And I want to test values into my derivative in between all of these places. This would be a great one to use your calculator just because our function that we're using right here that we're plugging these values into is so not cute. So if you have your calculator, you want to just store these values for x and then type them into your calculator. All right, so first one we have f prime. I'm going to do -1. Okay, that gives me -2. So this part is going to be negative decreasing. Okay, next I'll try, how about 1/2 between 0 and 1? That's -0.79, so long decimal. So this would be negative decreasing. And then I will try, how about 2? That is 0.629, ... keeps going on. So this one is positive increasing. All right. So if you actually looked at this graph, it looks like this. Okay, I messed it up. There we go. So here's 0. Here's 1. The reason why we had a critical point at 0, if you notice here, it has a vertical tangent, so it's undefined slope at that point. That's why it was undefined at 0 in the derivative. Okay. All right, so let's write down. We have decreasing. So f is decreasing on -infinity to 1, increasing on 1 to infinity. We also wanted to talk about the extreme values. So the only one that we have is right here at 1 because it was decreasing up until 1 that started increasing. So that is an absolute min. So absolute min at 1. And there is no max because, as you can see from the graph, it just keeps going up in either direction, so no max. Okay, number 3, find the critical points of f of x equal to x squared minus 3 quantity times e to the x. Identify intervals on which f is increasing and decreasing. Find the function's local and absolute extreme values. Okay, so we're going to start again with the derivative. Okay, this one is going to be product rule. So we have derivative of the first times the second plus derivative of the second times the first. Okay, we want to set this equal to 0. I'm going to go ahead and distribute the e to the x for the second parenthesis. Okay, it looks like every single thing has an e to the x, so I can factor that out. Okay, now we're trying to equal 0. If you notice, the first part is e to the x. E is a positive constant. There is no exponent I can put on it that will give me an answer of 0, right? Because I'm basically multiplying e's by themselves. So that's never going to give me 0. So that is out in terms of trying to help me equal 0. All right, so on the other side of this, it's a quadratic. And that means I should try to factor it. X plus 3 minus 1. Okay, so these are my critical points. So I want to make a number line with a -3 and a 1. And now I want to plug values in to the derivative. Again, great one for your calculator. I'm sorry if you didn't bring it home because it's just kind of a weird function. So I'm going to use this part right here. Pretend I didn't cross off the e to the x. All right, so let's try f prime of -4. That actually gives me a positive number. So at this side, it's going to be increasing. Okay. Let's try 0, f prime of 0. It gives me a negative, so this part is decreasing. It doesn't matter what value you pick in the interval. And then the last one, how about 2? That gives me a positive, so this is increasing. All right, so let's write down. We have f is increasing on -infinity to -3 and 1 to infinity, decreasing on -3 to 1. Okay, now look, we have increasing, decreasing. That means -3 is going to be a max. Here we have decreasing, increasing, so 1 is going to be a min, okay? You do want to take a look at the graph to see, are they absolute or are they local extreme values? Okay, so I'm going to sketch the graph for you here. Okay, so it looks like this. Okay, so it looks like at -3, I have a local max. Okay, there are higher points, but it is the highest one around. So local max at -3. And then it looks like at 1, I have an absolute minimum because 0 tends to be a horizontal asymptote here. So this graph kind of hugs 0 as it goes out that way. So this is an absolute max, or min, sorry, at 1. Okay. All right, so you guys have homework for this section, and then you also have 3.4. 3.4 is just a practice, so there's no lesson for it, but you do want to get that done. And I will be talking to you guys all about all of this stuff very soon. See you soon.